Let's begin. Hi guys, hope everyone's okay. Let me just resize some windows over here a second so I can see everything. There we go, cool. So we've got here, we've got Mr. G, Andy, Giampopo, Foray, Amok, Stepz, Colt, C64 Mark, Prince Phase. Have I missed anyone? No, I've not missed anyone. Hi guys. Oh, you having problems with your computer, Colt? Yeah, it is a pain when you don't have parts. Thankfully, I've got lots of parts now. I do have a spare power supply as well, but I have a feeling you're not close by to me. Hi, Sinno. Welcome to the stream. So yeah, we're going to go back to the very beginning, kind of right back to the stream I did, my first stream I did last year, to go over the very basics of assembly language. So we're looking at it from the point of view of 6502 assembly and the C64 in particular, but the concepts do apply to most assembly languages. Sorry, excuse me, still feeling a little bit iffy, but I'll get through, it's fine. So where do we begin? Okay, so what is assembly language? Assembly language is basically a text representation of machine code. You call for haze and he appears. That's amazing. It's like a summoning spell. And so what's machine code? So every CPU in every system, correct me if I'm wrong, I don't think there are any that don't run machine code, And machine code is just a list of instructions. It's a big long list of memory locations containing instructions. I'm going to open up the C64 debugger. I know it's not the friendliest thing to look at if you're not familiar with it, but it'll give you a bit of an idea what I'm talking about. So this is the Commodore for those not familiar, and this is the start screen. And right now this is running assembly language, and this is the assembly language that it's running here in this window. Doesn't matter what it means at the moment, we'll get to that at some point. This window here is the memory. So on the Commodore we've got 64K of memory, that's 65,536 bytes of memory, and each one of these bytes of memory contain a single integer value from 0 to 255, and they run all the way down here. You can see there's a lot, and everything that you see on the computer is running instructions in this memory. So the cursor flashing here, the fact that we can type things in, is all just a program that's running in memory. It's all machine code, and that's the same for every language, no matter. Some work on TTL, but I'll shut up now. Okay. No matter what language you run in, they will get compiled down at some point into into machine code. Assembly language is just a way that we can see that, because if you look at this piece of code here, for instance, that it's running through, this here is the text representation of it. This is the hexadecimal, this is the machine code, and you can see it's a bit harder to understand hexadecimal numbers like that than it is to understand this. So let me demonstrate a very, very simple, this is how I used to do machine code, so ignore what I'm actually doing here. This is just my start address. Let me just save this. So, oh, I don't want to save it in there. So this is how I used to write assembly language back in the day. I didn't have an IDE like this, so I used to write it on paper first. So I do something like this is changing the border color. So I used to write it down like this. Now this is the equivalent of, in BASIC, using pipe. I can't use that because I've got my joystick turned on. Oh, I still can't use that. That's weird. Oh, don't tell me it's crashed already, seriously. So most 8-bit computers from the side, in fact let me do it in the emulator. Most 8-bit computers from the time had this poke command, which allowed, it's still not working. Oh god, this is a good start, isn't it? Hang on, let me turn the joysticks off in here. There we go, right. So you'd have this poke command, and this allowed you to take a memory address such as this and put a number into it. So this is basically taking one of these memory addresses that we can see in here and putting a number into it. and in this case turns the border black. And this would be something you'd see in basic programs all the time for setting colors and things like that. Now obviously this is a very, very slow way to do to put things into memory like that, and that's what our assembly program does. You just turn your joystick on, or in here. Oh, it's off in here, that's fine. So what I used to do, I used to write the assembly instructions down on paper. So we won't go into what these instructions are. There are other videos that go over this. We will go over a few of the basics towards the end of this this stream, but for now, don't worry what they mean. Basically, this is doing the equivalent of poking a value into memory. But I didn't have an assembler, so what I had to do is I had to convert these myself into instructions. So I'd use a program in BASIC to basically do the pokes that you can see here, to poke the values for these directly into memory. So let me just show you how I would do that, and then I'll go over what it actually means. Let me grab up my... So I had the programmer's reference guide. I can use this now. So, and I'd look up the instruction that I wanted. So in this case, I want this instruction here, and I put that. Then I put the value. And this was a very, very long process, as you can imagine. So when I got an assembler, I was incredibly incredibly grateful. Actually, that's the wrong one. It should be A9. I'll explain what these numbers mean in a second as well. Where's my window gone? There it is. So then I want this one, which is 8D. And I think this is 60. I'm just going to double check there. Yeah, 60. Okay. And that's what my assembly language programs looked like on paper. I would then write a basic program to poke these into the right area of memory. So if I just load that up now, you'll see nothing really happens, but if I go and have a look in memory, that oh god, I've completely forgotten how to use everything. There we go. You probably can't see this very well. Let me try and... Yeah, it's not going to zoom in. But if I go and have a look at memory at that location, you can see here the values that I've typed in here appear in memory at that location. Let me run it in the debugger, it's a bit easier to see. The debugger needs a debugger. Oh, what? Wow. It's just crashing all the time. Okay, maybe you can't do that from the thing. Okay, fine. We'll do it from here. So yeah, if I look at that memory location, it's put these bytes in here, and these bytes are just a list of instructions. But you can see it doesn't do anything, and that's because we need to tell the Commodore to actually run the program. And that's what this address is here. This tells you which memory location the program is at. And the command for that and the Commodore was SYS, and if you do SYS 49152, it runs the program. So what's actually going on there? Okay, so every instruction that we type, so this is an instruction. The 3-letter codes that you see are the instructions. These are all instructions. Each one of these can either have no parameters, so no extra numbers after it, in the case of this one. One number, in the case of this one here, that's 1. Or 2 numbers in the case of this one. And that looks like this. So that becomes this in memory. That becomes this in memory. And I'll explain why these numbers look back to front in a minute. And that becomes this in memory. And if I run that, and go and have a look in memory, you'll see exactly the same thing there. And again, it's quite hard to see because the window is very small, but you can see there he's put these numbers into memory exactly as we specified with the original code. And again, if I type SYS 49152, it will do the same thing. The debugger is buggered. Yes, it is. It's not working very well. So, how do you know what to put in these locations or where to put them? So the way the Commodore runs, and the way most computers run, is they have a thing called a program counter. So if you look in the debugger, again, I apologize for how confusing this can look at first, but this whole block of numbers up here is the important bit. This is the processor status, basically. These are the processor status flags, which I'll cover shortly, but the important bit that we need to look at is this program counter, and this tells the 6502 where the next instruction is in memory, or where the current instruction is in memory, should I say. Oops, it's going to crash now because I've jumped to an incorrect place. So at any point in time, the C64 or any computer that runs on machine code, which, as I say, I think is most, will have this program counter which points to an area of memory. So at the moment it's pointing to, if I just pause it, actually you can see, so it's pointing to this location E5D4. These are hexadecimal numbers. I'll explain that again in a minute as well. But basically they map to one of the memory locations, and you can see in this memory location we've got F0 and F7, and this is an instruction called branch if equal, and it has this parameter to it. Probably not the best example because this is relative addressing and this doesn't look like it matches, but trust me, it does. This program that's actually running now is called the kernel, and what this is doing is handling things like flashing the cursor, waiting for text input, things like that. So everything that runs on the computer, including the input, the kind of initial screen, or the kernel, runs in this machine code, and that's what it's doing here. When we type SYS in here, let me run this program again. Oh, I've just deleted all of that. There we go. When we type SYS in here and then give it a number, what we're telling the processor to do is finish doing whatever you're doing, and then when you've finished, set the program counter to be this location in memory. So that means, going back to here again, I'm going to copy this code in because it is actually crashing if I try and run it. So let me just go to that location and type those numbers in. So A9 00 8D 20 D0 60, and then I'm just going to go and put a breakpoint there. So this debugger allows you to stop the program when it reaches a location, and you can see there it's listed the same code that I've written here because I've put those numbers in. It matches this code here, so I've told it when you get to this location stop. So let me just start running again. You see the program counter is still in the kernel area. If I type SYS 49152, as soon as I press enter, it will finish whatever it's doing in the kernel, and when it's finished doing that, it will jump to that location. And there you go, you can see it's gone pink here, which says it's jumped to that location. So this allows us to do the next thing, which is to step through the code, and we can actually see what it's doing at each point. So as well as the program counter, the CPU will have a number of registers. On the 6502 you've got 3 registers. We've got the accumulator, we've got the X register, and we've got the Y register. Different CPUs and different computers architectures will have different numbers of registers for various things, but the important thing to know is these are just like variables that you can store numbers in, and you can transfer numbers around. You can do addition, subtraction, and some systems you can do multiply and divide, and other things as well. So The important thing here is we're using this LDA instruction. This is going to load a number into the accumulator. It just so happens we've already got 0 in here, so I'm actually going to change this. I'm going to put a 1 in there, so you can see. And you can see as I type the 1 into the hex window, the instruction changes here. So if I change a number here, you'll see the value after the instruction is the 89. The value after the instruction will change, like so. Now if I press F10 again, it will carry out that instruction and then wait on the next line. So that's the grey line has moved down to the next one, so it's carried out this instruction. And if we look up here, you can see the accumulator register, this AR here, has indeed changed to 8. Which one's the hex window? Yeah, the hex window is this one in the middle, just slightly in the middle, to the left of the middle. Shall and squint, yeah, that's not me. That's far too light skin to be me. Yeah, and so pressing F10 again will continue and carry out this instruction. Now this instruction has 2 numbers after it, and that's because this instruction is referencing an address in memory. Now the confusing thing about the C64 and other 6502 systems is they use a number format called little endian, and what that means is, given a 16-bit address, that's an address that's more than 255, so 256 and above, or a memory address. You see these numbers down the side here, these are the addresses in memory. You can think of memory addresses as think of a long list of pigeonholes, basically, numbered from 0 all the way up to 65,535. Each memory address is one of these pigeonholes, and you can put a single number in the pigeonhole, and you can ask the processor what's in that pigeonhole by referencing its number, or you can ask it to put something in that pigeonhole. The STA is a store instruction, so it will store whatever we've got in the accumulator in that memory address. So you think of it like pigeonholes. It's saying look for pigeonhole D020, so I'm going to go down to that. So memory address D020, which is this memory address here, and store the value that we've got in the accumulator into that address. In this case it's 08, and that gets put into here. Now little endian means that this 16-bit address is split into 2 and reversed, which sounds weird. So this is our address D020, and it's made up of 2 8-bit sections. Hexadecimal is great because if you use hexadecimal, you go from 0 to FF. It's always 2 digits for 1 byte, which means if you've got a 16-bit value, it's just going to be 2 8-bit bytes like this. Little endian just means you put the little part first. The opposite is called big endian, which is where you put the big part first. But the key to remember is that on the C64 and also other 6502 systems, it's little endian, so you have to get used to putting the little part first. So anytime you use an address value like this, in memory it's actually going to switch this 20 and D0 around. Same, likewise, if we had something like that, in memory it's going to look like this. And you can see that in the debugger here. So you can see the address is D020, which is this address here, but in memory it stored the 20 first and then the D0 second. Takes some getting used to, but you will get used to it eventually once you've seen it enough, trust me. Oh, let me do a shall and squint for you. There you go. There you go. Okay, so if we execute this instruction now, there we go, it's gone down to the next one and it's stored this value in D020. Now, this is going to get a little bit confusing. So some memory addresses, particularly the ones to do with colours, will only change the lower number. So it's probably not the best example to show you. If I was to just let that execute all the way through and change this value down here, let's go to that. This is kind of C64 specific. So if I change this value to C020, it's not going to do anything, but when we run this program now, what we should see, well, we've seen the result of the first one, which is setting the border colour. Why can't I type in here? Oh, because it's typing in there. Okay. Let me type in there, damn you. Okay, it's not letting me type in there. Again, there we go. So there it goes. Run. It's stopped there because our breakpoint is still there. You can see it's got the value 8 already in there. So let's change that to a different number. Let's change that to 03. There we go. So you'll see as I run this instruction, the accumulator here, the accumulator register changes to 3. The program counter is now moved on to the next instruction, C002, and the next instruction says store that value at C020. So this is C020 here, and if I execute that, you'll see it changes to 3. And the final command is RTS. This means return from the subroutine. In this case, it basically just means go back to whatever you were doing before you ran this. So in this case, we were in the basic prompt, we ran this program, and this is saying just go back to the basic prompt again. And if we continue, you can see there it goes back and the cursor starts flashing again. So that's the basics of how machine code is interpreted in memory. And what that means is we can do some pretty cool stuff with it as well. So I know there was some talk on, worth mentioning, C64 is 6510. Yes, so 6502, when I keep saying 6502, I mean the 6502 family of processors. So 6502 was the kind of the language that was spawned from the first processor, and there's been lots of variants of it since then. So there's the 6510, which the Commodore 64 uses. There's the HC602 or something, the one that the PC Engine uses. Let me have a look. Try to remember what that is now. Hue something or other. Hang on. The Hue C6280. I'm going to type that in there. So that's the PC Engine one. There's a few others as well, but they basically all work on the same principle. The same kind of registers, mostly the same language. Just see if I can find some more variants of it. There's the yeah, I mean there's the 6503, 6504, 650. Yeah, it just goes all the way up to 6515. And then there's a few other kind of variants. The 1541 drive on the Commodore 64, for instance, has a 6502 in it. And you can actually run code on that, and that's how fast loaders work. They actually upload some custom code to the drive and run that. So yeah, so if you think of memory as just a big long list of numbers, and you think of a program as just a very specific set of numbers that mean certain things, then you can really see how it works. You're just pointing to an area of memory. Thank you for the follow. I can't read that. Oh, damn it. Hang on. Thank you for the follow, Puphead. Oh, and thank you for the follow, C64 Mark, as well. I missed that one. That must have been right at the beginning. Although I was away from the computer. Yeah, and that's the other thing to note as well, as Stepz says. These CPUs run at different speeds. So on the C64 it runs at about 1 megahertz. I think it's ever so slightly quicker on the NTSC version. And it's kind of balanced out because the NTSC runs at 60 frames a second. It has less lines on the screen, but that's a whole other topic. But they all run at slightly different speeds. It depends on the needs of the system. For some reason they thought the Commodore 64 was fine with 1 megahertz. And it is fine, we do well with it. So what this allows you to do in assembly, and this is quite unique to, well, not unique to assembly, but it's certainly easier to do in assembly than other languages, is to change this, because this is all just things in memory. What we can do is, if we write a piece of code like this, and I run this, you'll see what it does. I'll show you how we can make this change on the fly. Actually, before we do that, I'm going to show you how we automatically run something in BASIC. So one of the pain in the arse things is if you were to write code like this all the time, and then run this, you would then have to, every time you run it, you'd have to go in and type this, and it's a bit cumbersome to do that. So what some assemblers will do is they will give you a way of injecting some BASIC into the program. In Kick Assembly it's called Basic Upstart 2, which is not a very catchy title at all, but what it basically does is it creates that that BASIC program for you. So if I run this now and it quits, you see how the assembler, the vice automatically ran run at the beginning. If I list here, you see it's created a small BASIC program that does that, and that's what this instruction here does. C000 is 49152. If I change that to 49152, it will still run exactly the same. Yep, stream seems very stable tonight. Actually, I think I might be jinxing it a little bit by looking at that. It seems a lot more stable than normal. And even the BASIC program, if we go and have a look at the memory there, if I run this in the debugger now, it should work. Even a BASIC program is just a list of bytes in memory. I don't know why it does this on the debugger, but it always looks a bit weird when you run it. So you'll see if I go and jump to the memory location where our program was, you can see our program here. So it's setting the border color to black. So by loading the accumulator with 0, it's storing it at this memory location. This memory location basically is the color of the border. Whatever number you put in here, it will change the border color. We can see that if we go directly to that memory address. If I put a number in here, like 03, you can see I can change it on the fly. Note, as I said, that the things with colors in tend to, on the Commodore 64, ignore the kind of first, it's called a nibble, which is the first letter, if you like, in hexadecimal number. You can see as I change it, it's always getting changed back to F, but the lower bit, the 9, the A, the B, the C here that I'm typing in, is the bit that matters, and that's the bit that's changing the colour. And the border is D020 and the background is D021, like so. But if we go and have a look all the way back down, and we look in, sorry, let's just get rid of that. We'll go and have a look in this location here. On the Commodore 64, this is where BASIC starts. So when you turn the Commodore on, you get this 38911 basic bytes free. What it's basically doing is counting how many bytes are free between here and the start of what's called BASIC ROM, which is another machine code program which handles all the basic stuff, and that starts around about here. You can see there. You can see this is program that's running the BASIC interpreter. So whenever we type a command in here, a piece of code in this section gets run, and it handles converting that command into something that can be run in machine code. So at this memory location, we have some data here, which is our program. Basically, it is our. That is. I won't let me press enter on that. Damn it. Oh, it keeps going back to there again. Basically, when I press list, this is what it's reading. It's reading this here, and it's working out that this is our program. It's not too important what these bytes mean, but basically, from here to here, actually from here to here, is our basic program. Our basic program is the one that looks like that. That's the representation in bytes. And when you run that program, the the assembly program that contains all our basic commands looks at this, interprets it, and decides that this is an SYS command with the location 49152. You can actually see here just about in the side 49152, so those numbers are actually interpreted exactly as they're written. This 9E here means SYS. It's called a token. Every command in BASIC has a hexadecimal value attached to it, and that's its token. And this 0A here is the line number. It's actually these two numbers here. Again, it's kind of using a big endian format. Sorry, little endian format. So 0A is 10, so this means line 10. Cool. So with that in mind, we've got this small program. So this creates our little basic program. So this creates, I'm going to put a little comment here. Which just allows the program to run automatically. Now this is, as I say, this is C64 specific. If you're doing this on BBC Micro, Acorn Electron, the NES, the Atari 2600 or 800 XL, or the PC Engine, whatever, you're going to need something different. It all depends on your system. You'll have to look into user manuals, programmer reference guides to see how you can auto start your programs, but this is the most common way that it's done on the C64. Okay, so what it means that we can do, because these are just bytes in memory, is we can change these bytes on the fly. So if I run this program, as I said, the border will go black, the background will go white, like so. But what if we wanted to change this value here on the fly? Well, we can do that by loading a number in and storing that number in this location. Now we could just store it directly here, but I want to demonstrate how this works. So if we give this location a label, this is basically saying, I'll call it modify. This is basically saying use this name in place of the memory address that's here. So whatever memory address this is will now be labeled modify. And if I just put store that value in modify +1, that's saying store whatever's in the accumulator. So store this value here at this location +1. And we know that this is 2 bytes, so it will go, let's copy this down here. So this is what it looks like in memory. So this is saying take the number 3 and store it at modify, which is this byte here, +1, which is this byte here. So it looks a bit confusing, but let's run through. So I think it's important to understand colour does not have a U. Stop it. Dearie me. It's important to understand self-modifying code because it will help you understand why things crash. It will help you to write very efficient code as well. You can see there the border is the background has changed for different colours. So instead of it actually putting the number 1, it's now put the number 3 in there. So let's run that in the debugger and show you what's going on. Yeah, I unfortunately learnt most of my English from programming books. So when I type programming type words like colour, I will tend to use the American spellings. Is using, like, if you write words like surprised or realised, do you use Z or do you use S? Because I always use Z. Is that an American thing as well? I think it might be. Okay, let me put a breakpoint into. Actually, I need to put the breakpoint in before I run this, don't I? Because okay, one thing you can do as well is you can type .break, and it will just stop at that location, which is really handy. So there we go. This is the code that's at that location now. You can see in the debugger. Oops, let me make sure it's. Oh, it's still following it. Oh, it's because of that thing. Okay, I need to get rid of that. Oh. There we go. Right. So you can see the code here. This is the code that we originally typed here. And you can see how this modify label here has been converted. So it doesn't say modify, it says C00B, but you can see the label modify here. And modify is at C00A, but we put modify +1, so it's changed that to C00B, and that now points to this memory address here. And you can see here, where is it? There it is. So you can see here, we're telling it to store the number 3 at this location, and that is this here, this 01. So watch what happens as I step through this code. So store the border color. You won't see an update on here. I'll explain that in a second why you don't see that straight away. But this is the important bit now. So load the accumulator with 3. You'll see the 3 appear up here. There you go. And now it's saying store it at C00B. Well, C00B has got our code in it, and it's this 01 here. So when I press the button now, you see it change to a 3, change from a 1 to a 3. It's called self-modifying code. So this allows us to make changes to the code while it's running. It's a very powerful tool and something you'll use as you kind of progress with assembly. You use it to write very efficient code. It can also be a pain as well. It can cause crashes because if, for instance, I went to modify a piece of code with an instruction number that doesn't exist. So going back to my list of instructions, this here is a table of all the instructions. So we've just done loads, which are these ones here. We did this one, load a value, which is A9. But you can see there's some ones that are coloured grey, and they're called illegal instructions. Some of them are some of them will do something, some of them will just crash. And these ones called kill here do exactly what it sounds like. So if I put 02 in the place of where an instruction should be, so this next line, C00C, is this one here. You can see it says 8D there. If I put 02 there, you see now it becomes the kill instruction. And this no longer makes any sense. And actually, if I try and run this, you see it causes what's called a CPU jam. Let me just check that. Oxrom has a good question for Shallow 50k. Let me just say thank you for that follow. Thank you, Keebs and Trees, for the follow. And let me catch up with that. Code that did change though, so it's polymorphic. Yes, kind of. Yeah, I guess it is, yeah. In AirJury channel mods are not so picky about spelling. I'll never use self-mod code, never, never, never. See, you say that self-modifying code is dangerous. The reason I'm showing it now is because it's a really good thing to help you understand how code is actually running in memory. Your code is just a sequence of numbers. It's not instructions like you type it out. The computer just sees it as a big long list of numbers, and it's just jumping from one number to the next. So you can see in this instance, by changing one of the numbers, we caused it to put an invalid instruction here, the kill instruction. And the kill instruction literally just causes a CPU jam. It stops the computer from working. And you can see here, oh, actually it carried on for some reason, but sometimes it won't. You'll get all sorts of weird behaviors. Let me jump to that location again. In fact, it has changed that number again in that location. So if I put 00 in there, that's a break instruction. So now if I try and run that, oh God, I wish this debugger would work properly for me. Well, I'll tell you what I can do. I can just jump to that location. There you go, right. And when I run this now, it has actually jammed up now. So assembly language is just to allow people to not have to type in loads of numbers. Yes, exactly. So as I showed at the beginning, you could just type in the numbers like this. So if I really wanted to, I could write a program just by doing this. But obviously this is slow. It's really difficult to understand. And you're not going to be able to write very good code like that, but this is basically doing the same things that are down here. So assembly just allows you to kind of give yourself a textual representation of those commands. So it's important to understand that when you type a command, what you're actually doing is telling the assembler to put a couple of bytes into memory. It's 1, 2, or 3 bytes depending on the instruction. So RTS is just a single byte. This load command here in this particular addressing mode. If you don't know about addressing modes, it should have really been the video that followed this one, but I kind of did it first. So it's last week's video, and it goes over the addressing modes on the 6502. Is that because you jumped into a null? It's because the program counter, when it finishes running an instruction, it just goes to the next line. So I could achieve the same effect by doing this as well. If I put a byte there, like so. In fact, let's run that. Let's show you what happens here. So let's get rid of this self-modifying code. And let's just put a byte in the middle, and we can see what that's doing. Hopefully the music's alright, guys. I've tried to keep the volumes at the right levels tonight. And I have got a nice video from Stepz that I'm going to try next week. I didn't have time to do it tonight. So you can see here now, I put this 0 instruction here, and the BRK is basically an instruction that, yeah, it's an unsupported opcode. It just causes a crash, as Andy says, usually causes a crash. I think it does in most cases, actually. But all the program counter is doing, you see it here, every time an instruction is run, it jumps to the next instruction, so it knows that the LDA instruction takes one single number after it, so it knows that the next instruction is 2 bytes ahead. And it knows that after this instruction, the next instruction is 3 bytes ahead, and it knows after this one is 2 bytes ahead. And then when it gets to here and it tries to execute this instruction, it just kind of jams up. In fact, it's not jammed up this time, it's just done a weird crash. This is quite a common crash that you'll see on the C64. But it's a very unpredictable instruction. You don't hear music. Okay, let me give it a tiny little bit of a boost. I'm trying to keep it down a little bit. There we go. I can see the bar flickering, but I wasn't sure if it was loud enough. So assembly, yeah, so assembly is basically just a way to turn something that's human readable into a list of numbers. The numbers, the format that the numbers in isn't really important. I mean, we use hexadecimal mostly because it's nice and easy to work with 8-bit numbers. I can tell looking at any number if it's 8-bit or a 16-bit. So this is, I can tell that's an 8-bit number. I know that's a 16-bit number. But if you were to look at the same numbers, you know, these are the same numbers in decimal. It's hard to tell if it's 8-bit or 16-bit because you have to actually think about the value of the number in this case. So I know this is 8-bit because it's less than 256. I know this is 16-bit because it's more than 256. Whereas with hexadecimal, it's just how many digits are in it. So you think of every pair of 2 digits as an 8-bit number, like so. So that's why we use hexadecimal mostly. It's easy to tell, Shallan. What do you mean? Hex is just a numeric representation of what's stored in the RAM chips. Yeah, I mean technically in the RAM chips it's going to be in binary. But you say that, Hayes. If I was to give you a number, well, let's type a really long number in. Well, how many bits do you think that number is? Well, I can tell you that is a 64-bit number, and that's easy to tell because in hexadecimal it's this value here, and that's 1, 2, 3, 4 pairs of 8 bits. Sorry, 32 bits, not 64. 32, yeah. I was counting single bytes, single nibbles. Yeah, so I mean that to me is a lot easier to tell. Just because it's got F's and A's in doesn't matter. You just split it up into groups of 2. Each one of these is 8 bits, so it's 8, 16, 24, 32, and you can't tell that easily from the decimal representation. So yeah, as Andy says, the numerical representation of what's in the chips. So the chips will actually store it as binary, or more accurately, they will store it as a series of transistor switches, which are either in an on state or an off state. So binary is why we talk about computer kind of memory like that, because binary is on or off. So the memory chips on a C64, if you look at a C64 bread bin, there's 8 memory chips. Each one of them contains 64 kilobytes of 1 bit. So you look at this number on the chips in memory. There'll be one chip with, say this is memory location 0. Okay, that means that the very first memory location on that chip, the very first transistor on that chip, the switch will be on, and then on the next chip the switch will be on, and then on the next chip the switch will be on, and then on the next switch the chip will be off, and so on all the way across. And that's why you have 8 memory chips in the bread bin. On the C64 it's a little bit different. On the C64C they're 4K chips, so each chip has 64K of 4 bits of memory, so it stores first 4 bits in one and the other 4 bits in another. Yeah, so when you're executing the code, you're actually changing the values inside. You're turning the little switches on and off in the RAM chips. And so this is one way to look at a number. It's quite difficult to read binary. It has its purposes. There are times when you might want to look at binary. I'll go into that in more detail in a later stream where we do things like the logical instructions, but for the most part you'll want to use either hexadecimal or decimal. Like I say, I tend to use hexadecimal because to me it's easier to work with this as a kind of halfway between binary, because this is made up of these 2 pieces together. So this is the upper 4 bits, which is these bits here, and this is the lower 4 bits. So I can still visualize it as 2 kind of separate sets of bytes. Whereas with the decimal representation, sorry, that should be that. With the decimal representation, which is, if it gives it me, I could have worked it out by now. It's hard to split that up, so sometimes you'll use decimal though. There's nothing wrong with it, but essentially every instruction is putting a number into memory. So yes, that's true. OX-ROM. Actually, there is security research done to do things like that as well, to affect programs by sending kind of EMF pulses and things like that to cause problems and to break security on certain things. One of the so the company I work for deals a lot with random number generators using hardware. So when you generate a random number on a computer, generally it's not truly random. It's using some kind of formula to generate random numbers, usually as an exclusive OR shift or something like that, combined with some other trickery to make it seem like you're getting random numbers. But the company I work for needs true random numbers, so they have a piece of hardware that can do that. But there are ways to affect that hardware remotely by bombarding it with noise, and basically forcing it to kind of narrow the range of random numbers that it can pick. And that has major impacts on things like bank security and stuff, because bank security uses these kind of hardware number generators to generate your secure session keys and things like that. But anyway, that's a whole other topic. I could talk for ages about that stuff. I know Colt likes that stuff as well. In fact, I think it's Colt's job, isn't it? I think I'm still trying to make it my job. EIP. I'm not sure what you mean by EIP. Where Where is EIP? Oh, the stack. Okay, so this is... Yeah, we'll talk about the stack in a second. Yeah, it had two... No, it was two... they were 64K by 4 bits, so they're actually called this when you go looking for them. That's what they'll look like. You can tell from the number on the chip as well, so you get... I think it's 4164. These are 64K 1-bit chips. And then there is the 64Cs, which are 4464s, which are 64K 4-bit chips. But yeah, that's we can. I should do a stream actually on the internal workings of the Commodore, because it is quite interesting. It does kind of help you understand things. So far we've talked about how the program runs in memory. We've talked about what the processor counter is, the program counter is. So this is like this is what this grey bar is basically, and why the code is flicking around. I can look through the code, but the grey bar is showing which piece of code is executing. This is where the program counter is. You can see it up here flickering around. If I pause it, I tell it to follow the counter around. You'll see as I step through the code, it jumps to various locations and does various things. In this case, it's just kind of flickering around this area. Eventually it will jump to somewhere else. See, there you go, it's jumped to a different location, because we have timers that will check for whether the cursor should flash, whether to check for keyboard input, things like that. Again, all just assembly language programs. Let's talk about the other registers that we've got in here as well. So we've looked at the accumulator. This is kind of, on the 6502 at least, this is the one that does the most of the work. I've heard it also called the Arithmetic Register. Its true name is the accumulator. Some people like to call it the Arithmetic Register because it is the one that lets you do addition and subtraction. If you ever want to add two numbers together, you have to do it in the accumulator. Thank you for the host, Hayes. And then you've got two more registers that we can use using instructions directly like this, and these are the X register and the Y register. These are what are known as index registers. They're called index registers because generally they're used for the indexed addressing modes. Again, a topic that I covered in the last video, which I think is on YouTube now. Thank you for the follow, Passepartout. I'll call you Pasp. The registers are on the processor, yeah. So these, this whole bar up here is things that the kind of processor just keeps a record of. You can think of them as kind of special variables that are only used by the processor. There isn't a memory location that applies to these. They're just registers. They're just kind of holders for numbers that are temporary holders for numbers that aren't stored in memory. You can think of it as like the if you were to move something from one box to another, it would be the object that you carry that number in. So if it's pigeonholes, right, and you've got a postman moving around, postman is the register, so you've got three of them. You can give them one thing at a time, and they can either give that to each other, which is called transferring, or they can store it in a pigeonhole, or they can go and take something else out of a pigeonhole. So the registers are just kind of like placeholders for numbers. The index registers, unlike the accumulator, can't do addition and subtraction. They can increment and decrement, and by that I mean they can go up by one or they can go down by one, but they can't do much more than that. They can be loaded with values from memory, they can be loaded with numbers directly like this, and so this is perfectly valid code, as is this. They can be stored in places in memory like so, and they can also be transferred around. So we have commands like TYA. What that means is transfer the value that's currently in the Y register into the accumulator. So if I just run this program, you'll see that in action. So let me close all my debuggers down, put a breakpoint in here. So this break command just tells the debugger, stop what you're doing, show me where you are. It stops it from running immediately. There you go. Oops. Let's go into this mode. It's a bit easier to work in this mode. Yeah, it's the man running around in the human resource machine. Exactly, yeah. I will recommend that as well, because I don't know what your opinion of that was, Hayes, but I found it really enlightening as a game. It's what got me back into assembly language. So I hadn't touched assembly for 20 years or so. And then I got this game on the Switch. I believe it's available on Steam, on Android and iOS as well. But it's a great little game. And actually I'm going to use this video to explain the different concepts here. So I'm not going to put the sound on, there's no point in it. So basically this game teaches you the basics of what's going on in assembly language without ever calling it assembly language. And basically every level you get a little challenge that you've got to do. So let's have a look at the first challenge if it's going to load. Let's move it on a little bit so we've got some. Yeah, there we go. Right. So let's do it with numbers though. I don't want to get too confused. Here we go. Right. So in the analogy of a computer, these spaces on the floor marked 0, 1 and 2, this is your memory addresses. So in this case you've got a 3-byte computer. These numbers are just numbers, and you can see the number 3 has been stored in this memory location here. This guy would be the equivalent of our accumulator. He's the guy that's carrying the numbers around. So he's been told to load his accumulator, load himself with the number 4, and then he goes and stores that in a location. Actually, he's adding it to another location. But he's basically, this is the analogy of the accumulator. So this little guy running around, he's the accumulator. He's the one doing all the adding and subtracting. And it's a brilliant little game. I'd highly recommend it. And basically what you're doing on this side is you're using kind of block program, very simple drag and drop block programming to create assembly programs. And it does get incredibly complex later on. Yeah, 7 billion humans was the second one. 7 billion humans is really good if you do anything with multi-threaded programming. 7 billion humans is really good because it really makes you think about how threads interact. Where are these registers? They're on the CPU, yeah. Yeah, Visual 6502 is another one as well. If you want to see what's actually going on inside the chip. So we talked about memory chips having transistor switches turned on and off. Visual 6502, that's not it, is it? I thought that was it. Maybe there is an animated version of it. I think it's that one. No. Here we go. This is a kind of representation of the CPU. Actually pretty much how it looks. I mean, it doesn't look colourful like this, but the colours represent the different states. But this is a 6502 chip, and you can see when we run code, you'll see how all the switches light up. And this is all the various parts of the CPU turning on and off to allow certain instructions to run and to read things from memory. It's a very, very nice tool. I think you can zoom in as well. There we go. You can see how each of the pathways in the CPU is being activated as different codes run. As well, zoom out X, there we go. And you can step through one step at a time and see what happens. it helps if you kind of understand a little bit about what's going on inside the 6502, because otherwise, I mean, it just looks like a load of flashing lines. But it's really interesting nonetheless, and I would recommend, if you're interested in this sort of thing, checking out the actual architectural diagrams for the 6502 as well. There's plenty of links. There's probably links on here actually to them. Hardware manual. I think this is the one that's got the. Oh no, this just explain. This is just kind of base level explanation of it. But there's lots of things out there. There's also was it the Big Moss 6502 project that somebody was doing? I posted a link to it the other day. This one, yeah. So somebody's created a massive transistor scale replica of the 6502. They've stuck LEDs on to show the various areas line up, but this is actually a 6502. It runs about 50 times slower. Runs at like 1 hertz compared to 50 hertz. Well, not 50 hertz. It's 1 megahertz, but it runs at probably about 20 hertz or something like that. So it's quite slow. But you can see it in action. You could technically connect this up to something and make it work. It wouldn't work on a C64, unfortunately. Wouldn't work on many 6502 systems because it relies on precise timings. But it is a really nice thing. I do kind of want to get one, but they are very expensive. So, but you can see how it all works. You can see all the counters moving up and down. And on that chip is the accumulator, the X register, and the Y register as well. But yeah, I definitely recommend this game if you want to kind of get the mentality of 6502 programming, or just assembly programming in general. This is a really good game. I definitely recommend it. It'll start to make you think about problems in a very simple format, putting numbers in boxes, taking numbers out of boxes, adding numbers together, shifting numbers around. And all about branching. You see here we've got jump if 0, jump if negative, all things you'll use in assembly language. TIS 100, yeah, that's another good game actually, but I think that's probably a little bit more, that's probably geared more towards programmers, I think, whereas I think Human Resource Machine is the sort of thing you could pick up if you didn't know any programming at all. Pardon me, any programming at all. Right, I'm going to take a quick break, guys. When I come back, we'll talk about the stack pointer next, and what that's about, and how that works on the Commodore 64. Again, this is going to be different on different systems. I know the stack pointer is the same on the C64 and the NES. I'm not sure about the Atari. I'm guessing it probably is, because I think it's probably coded into the 6502. But I can explain how that works when I come back. All right, I'll be 2 minutes, guys. Be right back. And I'm back. Thank you for the follow, M Magdai, OXROM, and GKMNG. I'm going to call you GK. Not enough vowels in there. In fact, there are no vowels in there. Let's catch up on some of the thing. Do I have an explanation of Sublime Kick-Ass C64 debugger integration somewhere? Yeah, if you join my Discord, let me just put the link in here. There are some links in, I think it's in the Links and Resources channel. Let me just check for you. If you go to the Links and Resources channel and look at the pinned messages, there's a little bit of information in there of what I use and how it's set up. There's some instructions on setting up the packages. And if you have any problems, there's plenty of people in there that can help you with that as well. You should try Shenzhen.io. I did enjoy Shenzhen.io actually. There's another one as well. I forget what it was called now, but you made these little machines with pistons and stuff, and you had to kind of combine gems or some elements or something. That was kind of good. Hi, old school coder. You were on the Xbox. Oh, okay. And you're on the laptop. Is Kick-Ass much better than Relauncher? I mean, I couldn't tell you, to be honest, Marcus. Or I'm I've used Kick-Ass since I came back to the scene, and I just haven't looked back really. It's been perfect for me. Cool. Yeah, just, you know, feel free to ask on Discord. Everyone on there is really helpful, so if you do get stuck with anything, feel free to ask myself or anybody else on there. There's various channels. I do need to tidy the channels up actually. There's a lot of channels now. I should probably narrow it down a little bit. So let's quickly have a look at this piece of code that I started running and didn't finish explaining here. So we were going to look at this transfer instruction. So I said you've got the Y register, you've got the X register, and you've got the A register. You can actually transfer these values by using the transfer instructions. That's what this TYA is here. So as I progress down the list, I'm actually going to change the value in that location because all the values are set to 0 already. So, pardon me. So I've told it to load the Y register with 2. If I skip through, you'll see, perform that instruction. It's now put the 2 into the Y register. It stores it in the border color. The reason you don't see it on here is because the scan line, the thing that updates the screen, hasn't actually done anything yet. It hasn't gone anywhere and been able to draw it. If we go into this mode, you can see it has actually, if I move off, there you go. So this view in the C64 debugger shows you the current state, and it's saying that the current state is the border is red. This cursor is the actual scan line. We can see what code was running at any point on that scan line, but basically it means that the border has changed to red. We're just not seeing it yet because the scan line hasn't updated and hasn't rasterized that color to the screen yet. The next instruction is to transfer the Y to the accumulator. So you can see the Y is 2 here and the accumulator is 0. If we execute that instruction, the accumulator now has the number 2 in it as well. So we've copied that value from Y to the accumulator. Sorry, I just need to check that that's not something important that I'm missing. It's not. Okay, good. And then store that value in the background color. Again, you don't see it because it's not rasterized. You can actually see here it has started rasterizing the red border color. So the scan line is about here and it's starting to draw across the screen. If I go to that view, you'll see that color is now in the background as well, because we told it to do here. So that's the transfer instructions. If you want more detail about the individual instructions, if you watch my previous video where I talked about addressing modes and kick assembler, I do briefly cover every instruction, not in any detail, but I do try and explain. It's more about the addressing modes, but I do kind of touch on the transfer instructions as well. So the other register we've got that's important to know about is this SP. This is the stack pointer. So anybody who's used to programming in any language really will be familiar with the concept of a stack. So a stack is just, it's what it sounds like. It's a stack of numbers basically. You can think of it like, I like to think of it as a stack of plates. So with a stack, whichever number you put on is a plate and you put it on the top of the pile. Then if you want to take a number off the stack, you've got to take it off the top. You're always putting a number onto the top, taking it off the top. And that's what we do with the stack. Now, weirdly on the 6502, the stack runs backwards. The stack is in memory. You can actually see the values at 0100. So from here to, where is it? To here is the stack. So it's 255 bytes that fit in memory from 010 to 01FF. The top of the stack, the bottom of the stack, the very last plate in the stack is this address here, and the stack moves up like this. So it's actually running backwards in memory, but visually when you look at it like this, it is a stack that moves up the screen. So as you put numbers on here, the stack pointer will change. So the stack pointer is currently at F8, which means that the stack pointer is pointing to this location here. So this was the last number that was put onto the stack. If we were to put another number onto the stack, this stack pointer would move again to here, and so on and so on. I'm going to demonstrate that now. So if I put a number into the accumulator and push it onto the stack, and push it onto the stack, and push it onto the stack, and then pull it from the stack, pull it from the stack, and pull it from the stack, and then in the middle I'm just going to change the number here, right? You'll see what happens. So this is push a value onto the stack, this is pull a value from the stack. And it's always done with the accumulator, at least for this instruction. You can't do this with the X and the Y register. There is another push to stack instruction, but I won't go over that yet. It's to do with the processor status. Sorry, let me run this in the debugger. Make sure I close the other ones down. Okay, so here's our program. We're going to load the accumulator with 2. So again, if I press F10 to just skip through one command, or just execute that one command and we'll wait on the next one, you can see that the accumulator is now set to 2. Our stack pointer is currently pointing to F6, so let's go and have a look there. So that is here. So if I push a value to the accumulator, which is this next command, so if I press F10, you'll see it puts the number 2 into that location, and you'll see that the stack pointer is now pointing to here, to F5. If I press F10 again, it puts the value 2, because this is the value that's in the accumulator, pushes it into the stack, and moves the stack pointer. So now the stack pointer is pointing to here. If I push the accumulator again, the same thing happens. The number 2 is pointing to here. I don't know why the stack pointer isn't. Oh, it's because yeah, there we go. F3. So it's now pointing to here. I should probably not highlight it like that. Alright, put that back. There we go. So the stack pointer is pointing to here. The next command is load the accumulator with 3. So you'll see this value will change to 3. There we go. And now we're saying pull a value from the stack and put it in the accumulator. So if I press this, it's going to look at the stack pointer. It's going to say, okay, I need to get the last number that we put on the stack. So it's going to look one ahead to 0, 2. And it's going to put that number back into the accumulator. And you can see there, number 2 has gone back into the accumulator and the stack pointer has moved back the other way. The same thing will happen again. F5, so it's gone to here. And we can check that. So if I put a value like FF into the stack here, this is the next thing on the stack. The stack pointer is currently here. If I go to pull a value from the stack, it's going to put this value into the accumulator. So press F10, and there you go, FF has been put into the accumulator. Now you have to be careful with the stack, because the stack is used for lots and lots of things. The main thing that it will cause you a headache for when working with an assembly language is whenever you jump to a subroutine. So when we typed SYS, it's not going to let me do it now, is it? When we typed this into the I can't type in here now because it's trying to put it in here, that's why. Sometimes this debugger can be great, sometimes it can be a pain. So when I type this in, what actually happens, if we just pause a second, actually you can see it here. So there's the stack pointers are about F2, which is around about here. You can see some other numbers changing here, but the moment I do this, the stack pointer is going to change to something, and I'll show you what's going to happen. So if I press enter on here, which is now not going to let me because I've got this value in here. Oh, come on. It can be a pain to work with this debugger at times. No, it's still trying to edit that value in here, so let me... Oh, it's not going to let me run it. Okay, let me... No, I need to run it from here to demonstrate this. How do I prevent that? That's really irritating. I want to prevent it actually writing a number in here. Maybe if I press shift and enter. No. Don't know how to... Yeah, the C64 debugger is It is a great tool, yeah. It is a very great tool. Yes, you can mess with a stack pointer. I'll show you those instructions as well in a minute. I don't think I'm going to be able to get this to run. Actually, maybe if I go into this screen and do it. No, it's still trying to edit something somewhere. Right, let me try running it again and then just immediately typing in that window. So I'm going to let that code run through. There we go. That didn't seem to run. Oh, it didn't run because I wasn't doing anything special. Right, so I've run this program and it's paused, but you can see the stack pointer. It points to F6. So let's go and have a look at that location. Oops. So O1 F6. So this is the next area of memory. So what's important here is the previous two numbers. So the last two numbers that were pushed onto the stack is what the kernel. So when the 6502 runs and it runs a program like this, it needs to know where to go back to when it's finished running this program. So the way it does that is it stores the address on the stack. So the last two values are 46E1. So the location we're going to go to is remember, it's little endian, so it's actually E146. So if we just go and put a breakpoint on E146, which now it's trying to write over this side. Please let me work on this side. For the love of all that is holy. No, okay. It's testing me. It's really testing me. That's what it's doing. There we go, right. So I'm going to put, it says it's, now, this is the thing, when it says the return address, it's actually the return address plus 1. It doesn't matter why that's the case, just know that when it comes to return addresses in the stack, it's like that. So let's go back to where we were running the code, and let's just step through. So it's going to do the same thing that we saw before. It's going to take these values from the stack, take the values and put them onto the stack. So you'll see the number 2 appearing in here. See it there, and then it's going to pull the values back off the stack, and then it hits this RTS, and this is saying I've finished doing what I'm doing, go back to what you were doing. And at this point, if I skip just one byte ahead, you can see it's jumped straight to E147, and the stack pointer has now gone to here, which means it's read these two values, it's jumped back to that location. Now, why is that a problem when you're coding with the stack? Well, it's a problem if you push 3 values to the stack and you only pull 2 off. When it goes to do this return, you'll see what happens. Yeah, they should. The focus does get really janky at times. It's terrible. So let me. Oh, you can see it's crashed straight away. I should not have. There you go. Let's do it from here. So we can see we're at this location. The stack pointer is F6. So let's just move down to that in the memory view in here. So F6 is here, and you can see again it's pointing to E146. So it's pointing to that same memory address. Now, as I push things onto the stack. Oh, damn it, I've done it again. I need to press the right button. As I push things onto the stack pointer is going to decrease. It's going to basically, as it adds things to the stack, the pointer is going to move backwards through this block of memory, which is currently here. So F6, O1 F6. O1 is the stack area, and the stack pointer tells you where it is. So if I skip through, so I've added 3 numbers, so now the stack pointer is here, F3, see it there, and we've got the 3 numbers. Now when I pull the 2 numbers, the next instruction is return, but the stack pointer is now pointing to here. So instead of going to E146, it's now going to jump to 4602. So you'll see when I press F10, it's jumped, 4602 plus 1. It's jumped to this location, and you can see there's a break instruction there. So when I run this, it's going to crash. It's going to cause this kind of weird crash. Sometimes you will just get a complete lockup. sometimes you will get this kind of ready screen like this. Sometimes you'll get, depending on if you've been doing stuff with graphics, you may get garbled screen or all sorts. And that's because we didn't pull the same number from the stack. Thank you for the follow, Philadelphia Coins. Welcome to the stream. Yeah, I mean it's essentially it's you're jumping into the wrong place. Yeah. So instead of pulling the right return address from the stack, it's now pulling the wrong return address, because whenever you do these pushes and pulls, you should make sure that they match. So if you've got a piece of code, it's got 3 pushes in, there should be 3 pulls as well. It's not too important. I mean, it's important to get right, but you probably won't have to worry about it too much at first. But as you start writing more and more complex code, you'll start using the stack to push things so you can save things. So yeah, you just have to be very careful. If you do a push, you make sure it gets pulled later as well. Max stack is 256 bytes. It is indeed, yes. But you'll be hard pushed to reach that limit. What a lot of games do is they will use maybe 64 bytes, 80 bytes at most, and they will use the bottom half of the stack for something else as well. You have to manually keep track, but you can also manipulate the pointer. Yeah, so what you could also do, so there is another transfer command, and this is called transfer stack, and this only uses the X register. Don't ask me why, it just does. So if I transfer the stack pointer to X, the X register now contains that value. So if I go and run, sorry, not that code, run it in the assembler in here. And it's crashed again. Oh. Part of me wants to get involved in helping write this assembler, because it could be so much more. It's really, really good. I really like it. It needs some stability. It's got some issues. Alright, there we go. So the code is paused at this location. So first instruction, we tell the accumulator to load the value 2 into itself, which is doing there. Now the next instruction is transfer the stack pointer to the X register. So our stack pointer is F6, and you'll see here when I run this command, F6 now appears here. That in itself doesn't do anything, it just puts it into the X register. But what you can do is then I can push a load of values to the stack, like so. I could just pull 1 from the stack. Now this would normally crash, but if I transfer the X back to the stack, it will restore the stack pointer, and this won't cause a crash. So let me run that again. Thank you for the follow, TinySmall69, and welcome to the stream. Oops, I'm trying to grab the right window over here. I've got like a notification window that I keep everything on so I can see what's going on. So, right, let's have a look. So what's going on here? So, again, we load the accumulator with the value 2. So you see 2 appearing here. We transfer the stack pointer to the X register. So the X register is now F6. And then we're going to do some stack manipulation. So we're going to push a few values to the stack. You see the stack pointer changes to F3. We're going to load a value into there. It's irrelevant what this code is actually doing. It's just playing around with numbers. And then we're going to pull a value from the stack. So you see we grab that 2 that we pushed onto the stack and we grab it back. But now the stack pointer is pointed to F4. So if we were to just return from this code now, F4 is here. It would try to return to 02, 02 plus 1. So it'd be 02, 03. And obviously that's going to be some code that doesn't do anything. It's probably going to crash at that point. But this next instruction takes whatever's in the X register and puts it back on the stack. That's the wrong button completely. So you can see the X register is F6, and now the stack pointer is F6. So now the stack pointer is here, and that means that the next address the next address is the correct return address, and this code should just run perfectly fine. Push the accumulator into a stack. A isn't the stack. No, A is not the stack. No. when you push the accumulator onto the stack, you're basically, I mean, if you think about it as JavaScript, you can think of the stack as an array. So if I was to do this as JavaScript, it would be like so, and then to push the accumulator, so if we have a variable called accumulator, like so, then push accumulator onto the stack is the same as saying stack dot push accumulator, and pull accumulator would be accumulator equals stack dot pop. So that's the like the JavaScript equivalent of what's going on, and you can think of the stack pointer as that basically. So that's the kind of JavaScript analogy for what's going on there. You can effectively make functions that way. Yes, you can. It's not advised to kind of mess around with the stack pointer too much, but there are some clever things you can do with it. So for instance, if you've got so say you've got a main function here and you want to do some stuff here, so you might do so this is jump to a subroutine, do some stuff, and then you might want to jump to inner 2 and do some more stuff. Now the normal way you would get out of this is you return from this subroutine, which would take you back to this one, and return from this subroutine here. But sometimes you might not want to return to this subroutine. So say there's do some extra stuff here, and you make a decision in this one that actually you don't want to go back and do this stuff. What you can do is before you return, you can just pull 2 values off the stack. And now when you return, instead of jumping to here, it's going to jump back to this one, because this is the address that's on the stack. You've got rid of this one off the stack. So this is kind of like doing a break routine, for instance, to break out of that kind of nested group and go back. So there are some stuff you can do with the stack. I would not advise to mess around with it too much, but you can kind of do some kind of cool stuff with it. You can also manipulate it by forcing it to go somewhere else. So say you've got a main again, and you jump to it. Let me just undo that, it's probably easier. Say you've got a couple of routines here. You know, this might increase the border color or something. What you can do is sorry, inner 1 plus 1, push that onto the you would have to pull 2 values off the stack and then push a new value onto the stack, so you can actually change where it returns to. Sorry, main 2, isn't it? But I mean, this is getting beyond the basics really, so let's move on from this. But this would allow you to basically return to somewhere completely different. So instead of returning to this function, you could tell it to return to this function instead. The main use you'll find for pushing stuff onto the stack is if you want to store the value of registers. You probably won't need the stack for much more than that. The most common one is if you've got an interrupt of some kind. So interrupts can happen at any time, and when they do, you obviously want to restore the values of the registers. So what you can do is you can push the accumulator onto the stack. You can transfer X to the accumulator, push that onto the stack, transfer Y to the accumulator, push that onto the stack. Now you can do anything you want here with these values. You know, you can put anything you want into here. It doesn't really matter. Oops. And then when you return from this interrupt, you can just do the opposite and get all these values back again. So it's a way of just storing values so you can use them later, and then you return from your interrupt. But as I say, this is kind of advanced stuff, so let's move on from this a little bit. Tiny small comparing C64 with JavaScript is new to me. Yeah, I mean it is, but as I said at the beginning, all code ends up as assembly anyway. And sometimes there's coders who will know JavaScript or similar languages, and I think kind of JavaScript array access is pretty much the same in most languages anyway. So it kind of helps to understand the stack as an array like that, an array where all you can use is push and pop basically. Okay, push onto several instructions later. Yep, I thought stack would be something like 256 bytes of CPU cache. It's 256 bytes just in memory, so it's just this block of memory here from 0100 to 01FF. I mean, other than that, there's nothing special. It's not faster or anything. It's just the area of memory that the processor uses for its stack registers. Does an interrupt sit on its own thread or something that's part of a main while? It's not really threads. It's yeah, as Akmafin says, it's just one thread. So when an interrupt happens, it stops whatever it's doing. It finishes the instruction it's on there and then it jumps to the interrupt function. It runs that interrupt function, and then when that's sorry, not function, subroutine. When that subroutine is complete, it goes back to where it was again. Again, using the stack as a pointer to tell it where to go to. There is some clever stuff you can do with stack manipulation during IRQs to stabilize rasters. We've covered that in other tutorials before now. I think we did VSP scrolling had some stuff about stabilizing rasters, and that used transferring it used this TSX command and the TXS command to manipulate the return instruction from the interrupts. Okay, so the other thing we need to know about for assembly language is the concept of flags. So we've talked about registers, we've talked about the stack. The number of registers you have will depend on which system you're using. The C64, the 6502 is woefully woefully equipped with registers. As I say, you've got one accumulator register. If you want to call it the arithmetic register, by all means do so, but if you're talking to other people about it, call it the accumulator. They'll know what you mean a bit more probably, but you can kind of think of it internally. It is the one that does the arithmetic, and then the X and Y registers, which are your indexes, index registers, and the stack pointer. The other thing most processors have is the concept of processor flags. That's these zeros and ones here. They're called flags because they're either up or they're down. You think of it as a guy holding a flag up or holding the flag down. A flag down means 0, a flag up means 1. True or false, it's a Boolean value. The term flags is used in most languages for these kind of Boolean values. On the C64, flag generally means one of these processor flags. Again, this is something that's just stored on the CPU. This doesn't exist anywhere in memory directly, although you can again push this value onto the stack. So I'm going to quickly demonstrate that, and then I'll explain what the flags are. So let's just make a tiny piece of code in here. So this little instruction that I keep typing here, this is saying insert the code that's coming up next into this memory address. I'm using 49152. You can quite as easily just use a label, and Kick Assembler will just work out what that address is. But I'm going to keep using this so you can get the concept of it going into memory. C00 is, as you can see if I'll highlight here, there we go, 49152. And the reason I keep using this area because it's the first piece of memory that I actually wrote assembly programs in, because BASIC fit into the space from so BASIC takes up the memory from here to here, and the top half of this, so from there to there, is the basic ROM. It's called. It's the code that actually runs BASIC, and so that means you have this amount of room to put all your code into, and that room is that many bytes. That's how many bytes free you've got, which you will have seen every time you boot the C64 up. It's actually a good indication that your memory's gone bad, because of the way the memory's arranged in the C64. Like I said before, it's a 64K chip with either 1 or 4 bits on it. If any part of that chip goes bad, then you lose some of your bytes here, and you will see that value change. If you're lucky, you will see it change. If you're unlucky, you will see crashes of other kinds going on. But if you ever boot your C64 up and it doesn't say that, it means you've got a bad RAM chip. So the reason I put my code into C1000, into here was because it was above BASIC. So I could put my BASIC program that loaded the machine code into this location. I could keep BASIC in memory, and I could just start putting code in here. Anyway, enough of that. So this is writing the little BASIC program that points to this location, and this little instruction here, star equals, is just telling Kick Assembler the code that follows needs to go into this location. So I'm just going to do a very, very simple piece of code now, which is PHP and then RTS. This isn't PHP the language, this is another stack command. It's called push the processor status to the stack. If I run that, oh, because I pushed it to the stack, that's why. Let me pull it from helps if I actually pull processor status from the stack again. There we go. That shouldn't crash this time. And see what I mean about if you PH something, make sure you PL it, or else you're gonna. If you push something, make sure you pull it, or else you're gonna get crashes. There we go. It's working. Let me put a breakpoint in there so you can actually see it running. Oh, that's a good burn, that haze. I like it. So this instruction pushes the processor status to the stack. So let's go and have a look at where the stack is at the moment. So F6, which is here. Oops. So the next value, oh no, here, sorry. The next value we push is going to go into this location. It's 0, 0 at the moment. This number up here is our processor status. This is a list of 8 flags. It's only actually 7 that do anything, and I think out of them, I'm not even sure. Oh, that's the interrupt. That's 0, carry, decimal. Can I remember what B is? That's the one I don't know what it does. I'm not sure what B does. It might be something internal. I'm pretty sure you don't need it, or I'm just being dumb and forgotten what it is. But the point is, it's stored as a single number in memory. We display it as binary in here because it relates to different things. Each one of these letters at the top means a different thing. It's a different name of a flag. B is only pushed to stack when interrupt. Okay. Okay. Interesting. I didn't know that one. So you see this number is 00100000, or in binary that would be, what's that? 1, 2, 32. So we should see 20 appear in this location when we push that value to the stack. So let's just skip that through. 30. Why is it pushed to 30? Okay, I don't think it's taken account of this number here, but basically it is pushing that value. It's pushing that processor status to the stack, and when we pull it, we should get it back again. The problem with the C64 is there's lots of little bits like this that you don't have control over, as I was saying with the colours before. With the colours, when you poke to a border colour or a background colour, or even screen colours, the colours of each of these characters here, it's only using the lower 4 bits. It's only using the second letter in this 2-letter hex value. So you see, I'll show again if I go down to D020. You see here, if I put 0, if I actually type 0, you see the 0 there. If I type 3, it's going to set the border colour to cyan, but look at the value when I've finished. it's just changed that back to F again, and it's because that bit is irrelevant. It actually doesn't exist on the board. Actually, I'm not sure about the border colours. I think it might exist on the border colour, it's just not wired up. But certainly in the colour RAM, which is this area up here, we have the same problem. If I type a number in here, it's changing it to 0, but if I type F2, it's always changing that first one to 0, and that's because the colour RAM chips are only 4 bits, so they only have this bottom number, they don't have the top number. So you can't use these for storing 8-bit numbers, you can only store a 4-bit number in here. Okay. If B is 0, it's a regular IRQ. If B is 1, it's a break command. Cool. Thank you, Ep1. I didn't know that one. Although it seems to be storing... I can turn it on and off like this, but it seems to be storing the wrong number anyway. But basically, the processor flags you can push and pull from the stack, and generally they will work. I mean, it seems to be pushing the wrong number, but I think it's just because of the way that the bits are stored in memory. So what are these flags? These flags are the results of operations on the CPU. So I'm going to demonstrate a couple of them now. I'll demonstrate... I'll do the Z flag first because that's the easy one. And then I'll demonstrate the negative flag and then the carry flag. And I'm not going to bother with the other ones. I might do a stream on those at a later date. So... if you keep doing ink, these are, yeah, it's perfectly fine. That's a common thing you will see. I mean, if I do that now, I'll show you. Oops. So this piece of code, we're just telling it to increase the border color and then jump back to the beginning, which will just keep increasing the border color. And that's how you get these flashy borders. As you can see the difference between what you actually see and what the actual status is. So think of this as a status window rather than like a true representation of what's going on. This is the true representation. This is just showing what's happening at any one point in the code. The whole thing changes color. Whereas here it's changing color. As soon as the scan line gets to it, it's drawing it in the current color and then skipping on. I said Z and not Z, yeah. Okay, so, and you'll see if we look at D020, you see the F never really changes. I think it does flicker now and again, but generally it's not actually. See, it's staying as F all the time, but you can see even though we're incrementing that value. It's also important to realize this as well, because if you want to do something like, you want to load that value, and then you want to check if that value, you want to check if the border is white, that's probably not going to work. Because actually the value you're going to get back is going to be this. And you can't guarantee it's going to be that. It could be that. It could be that. There's no guarantee what it's going to be. At least I don't think. I think it might change on different revisions. So you have to do something like this. But again, it's kind of going beyond what we're doing here. So I want to show you the processor register. So we'll start with the 0 flag, and there's a few things that change the 0 flag. I'm just going to show you some simple ones. If you want to know more, there is a really good... Oh, I've got it already open, haven't I? So this page, which I'll put the link to in here. Okay, let me explain that. So the color the color RAM on the board itself is only 4 bits. So even though the memory address that you reference is an 8-bit address, only 4 bits is actually wired up on the board. So you can see as I'm changing it there, only the bottom value is actually taking hold. And that's the same for all the color locations. The top 4 bits don't exist for those locations. So it's the same in the background color as well here. In fact, you can see here it's flickering between F and 0. So the only constant is the bottom 4. It's the only bit you can trust. So you will get kind of random flickers like that. So you just have to be careful when you read colours that you do an AND just to get the lower 4 bits. I don't know why they did that as well. I mean, I'm guessing it was a cost-saving thing to only use 4-bit RAM for those locations, because they designed the chip around the VIC around 16 colours, so they didn't need the upper 4 bits. It would have been nice to have them though. What would have been really nice if they'd have supplied, and this is going into the slightly geeky territory here, but if they'd have supplied 8-bit colour RAM and allowed you to switch between the upper nibble and the lower nibble for the colours, because then it would have been bufferable colour RAM, and it would have made all those scrolling tricks that we have to do to make Commodore smooth is to make it to make it smoother. You'd have been able to flick between the two instead of having to redraw all the colours on the screen in one frame. You could have buffered it, or you could have had 256 colours as well, which is what the Atari does. Atari 800 and 600, I think, have 256 colours, or close to that anyway. Okay, so let's look at the 0 flag. So, as I say, that link I just posted, bring it up again. This has all the instructions in it down here, but you can see, pardon me, you can see the flags here. They've got the same labels as they have in the debugger, and the little star in a column means that this flag can be affected by this command, and you'll see the 0 flag is affected by most commands. And the reason for that is because anytime you load a value, see here, anytime we load a value, it can change. If it's 0, then the flag gets set. If it's not 0, then it doesn't get set. Anytime we transfer a value, if the value we're transferring is 0, it gets set, with the exception of transferring the value to the stack. So only if we transfer a value into a register. So we're transferring to the X, to the A, to the Y, to the A, to the X. They can all set the 0 flag, as you can see here. Again, pulling a value from the stack because it's going into a register. Anytime you put a number into a register, basically, then you are going to set the 0 flag. Likewise, if you where is it? If you do comparison instructions, these can also set the 0 flag. I'll explain those in a second. For now, let's just skip. We'll just step through this code, and you can see the flag enabling. In fact, let me do the whole thing in here. So I'm going to write a few pieces of code here, and then we'll go through what's actually happening as we run it. Is that why I keep seeing we need to drop in FPGA replacement for the VIC-2? I wouldn't want to see that, actually. I think it's kind of, it would lose its charm. I think if you start giving the CC, it's like the Spectrum Next. My biggest problem with the Spectrum Next, right? I think it's a great piece of technology. I think it looks really nice, and for me saying that about Spectrum is you know, it's unusual, but I think it does look like a really nice piece of kit. And my problem is it's not a retro computer. It's just it's retro in its look. It's retro in the fact that it will run a Spectrum game, but so will my PC with an emulator. And you know, it's just you've given it all those colours. It's the same with the Commander X16 as well. They're just turning it into something modern. It's stupid. I don't like it at all. I get the Spectrum X for £10. Yeah, I must admit I wouldn't mind to see one. I wouldn't want to pay the amount that I have to do to get one, but I wouldn't mind kind of having to play around with one. But to me, it's not a retro machine. Just because it can run Spectrum games, it's styled like a Spectrum. It's not a Spectrum. It's a modern computer, just based around kind of some retro ideas. But it's got like crazy amount of colours and like high clock cycles, and also it's got all the things that make it not an 8-bit computer from back in the day. I do like the Mega 65, but that's because it is basically what Commodore were going to release. So to me, it's not adding anything that wasn't already going to be added. It's just kind of making sure that people can use the computer that never got released. So, okay, right, let's go through this. So, the 0 flag is this Z here. This is just 1 bit in a value. As I said, you can push that value onto the stack if you want. That's probably even less used than push the accumulator and pull the accumulator as well. So if we load the accumulator with a value 20, then obviously we're loading the accumulator with a value that is not 0. Apparently the 0 flag is set to 0 already, so let's just go and set that to 1. So we're saying that the value currently is 0. If I run this command, we put 20 into the accumulator, and why isn't that flag set? That flag should be set. Oh no, it's not 0. I should have done it the other way. Wait, no, that's... Wait, what's going on there? Have I broken it by doing that? I've broken it by messing with it. I shouldn't have messed with it. Let me run it again. Alright, okay, so it's saying it's not 0, and then I load the accumulator with 0. So the accumulator is now 0, so it sets the flag to 1. So you can see by putting a 0 into this register, it wouldn't matter if it was this, the X register or the Y register, we set the 0 flag. And you can see that if I set the value of the accumulator to 30, it clears the flag again. So it's the flag is the last thing we put in a register is no longer 0. Comparisons basically allow you to take a value, in this case in the accumulator, the CMP means compare with the accumulator, and compare it against another number. Now internally what it's technically doing is subtracting the two numbers. The result isn't stored anywhere, but what does happen is it will set these flags according to that result. So if I run this now, if you subtract 30 and 24, you get -6. Actually, it's the other way around. It's 6. 13 minus 24 is 6, which is not 0. So you can see the 0 flag is not set. We haven't changed the value in here. The value 6 is not stored anywhere. But you can see that it knows that the result was non-zero. However, if we compare the accumulator, which is 30, to 30, actually it would have been not 6 anyway, because we're talking in the hexadecimal here. If we compare their value in the accumulator, which is 30 to 30, and subtract them both, the result is 0. So if I skip forward one instruction, you see the 0 flag is set. So this is really important, because what it means we can do is we can do things like this. We can use those flags with branch instructions. So we have branch if equal, which means branch if the 0 flag is set, branch if equal to 0, and we can point that to a location, jump 1 or something like that. And then you can have the opposite, which is branch if not equal, which means if the 0 flag has not been set, then you jump to another location. So this is how we do basically if statements. So to give that in, let's go back to the JavaScript analogy here. So say we have a piece of code like this. Branch equal let's call it skip like that. We'll put a label here. It's RTS So what this is doing is it's saying load the accumulator with a value at 3000. So if we take the analogy of JavaScript again, let's just imagine there's a function called getMemory, and this takes a hexadecimal address. So it'd be something like that. So this is putting the value that's at that memory address into the accumulator, and then we compare it with 30. So we would say if accumulator equals the hexadecimal value 30, then we're going to do this, which is that's the equivalent in JavaScript. So you can see this compare and branch is the equivalent of doing an if statement. Right, I'm going to take a short break while you lot argue about argue about whether or not you want a 64-bit 64K machine. Yeah, I'm. You know what, guys? That I've ordered the Atari VCS, so I obviously like. I do like some systems like that. I'm not against systems like that, but for me, I wouldn't want to add anything more to the C64. I'm not going to catch up with the chat. I've been keeping an eye on it in the corner, and I can't be bothered with that. It's too much. It's too much. I like the idea of the C65. I do like the idea of the Atari VCS, just because I like the style of it more than anything else. I realise it's going to be an overpriced piece of junk, but I have ordered it, so whether or not I get one, I don't know. It's kind of a bit up in the air whether or not I will. But yeah, I like my C64 Pure. I mean, I've got a Turbo Chameleon, and I barely use it. It's nice to see a few things running on it, but I'm not massive. I would like to do something for it, just because I want to see what I can do given the power on the C64. But I wouldn't want to check. I think for me, the thing that makes the C64 is not the speed of it. It's the graphics and the sound. You change the sound too much, it's not a C64 anymore. You change the graphics too much, it's not a C64 anymore. I can handle, I need to change my headphone, the battery's going in this one. I can handle an extra SID chip because it still sounds like a SID, just more channels. But I wouldn't want to change the VIC chip because I like the limitations of the color palette, and I like the kind of the double width pixels and things like that. I like the limitations of the C64. It gives it its charm. Right, that's working, so I'm going to put that one back on charge. Right, I'm going to go and take a quick break, guys, and when I come back we'll have a look at some other areas of code. I'm just trying to think. I'll have a think while I'm having a cigarette what we can do next. But yeah, I'll be right back, guys. Be right back. Right, and I'm back. Is everyone still going on about that? I think basically what everybody wants is the Mega 65 because it's the best of both worlds. You can run C64 stuff on it. It behaves like a C64. You've got the stuff that Commodore wanted to put in the machine with a few modern kind of tweaks to it as well, but nothing that takes away from the C6 from the Commodore brand too much. So, all right, let's discuss what makes a program. So if you're looking at games, what you'll generally have, it's usually built up of three components basically. You'll have your setup code, which will do things like, I mean, this is very simple. You'll set the border colors to what you want. You may clear the screen using a loop to kind of loop through all the memory addresses. So again, the screen is just I can explain indexed addressing a bit, I guess, and I'll change that to loop so it doesn't get confusing. Oh no, actually I'll use this. I'll explain what this is as well. So this is a special type of label. It's called a multi-label. I'll explain that when we get to it. But to clear the screen, you're just doing the same thing. So if we look at this screen here, you see this grid that's on it. Every single one of these characters on the screen is just a memory location. and the default memory location on the Commodore 64 is 0400. This will depend on your system. I think most 8-bits of the era used a system similar to this. I haven't used very many of them, so I couldn't be sure how they all work, but the Commodore works like this anyway. So this is the screen here. Let's view it in this mode. You can see here, you can actually see the writing in this column here. So this column is a Commodore PETSCII representation of the memory, and so you can see quite clearly that this block of memory here is the screen. If I were to go and change one of these values, let's change this value here, let's change it to 39, and then run the program, and you can see I've changed this value here. So now we've got a Commodore that says it's got 938,000 bytes free. I mean, it hasn't, but I've just changed that value. And it's the same with any of these memory locations. I can put a character in the middle of the screen here if I want. So I can put an A. See it appear there. It's all just memory locations. So to clear them, I just have to put a space character, and you can see the space is 20. And the way I do that is I'll load the value with 20, and then I'll store it at the memory location of the screen, which starts here. I use $X. I'll explain what that does in a minute. And I do this over 1024 bytes. The screen's actually only 1000 bytes, but this is a very simple way of just clearing that memory. And what we're going to do is, this is saying store it at 0400 plus the value that's currently in the X register, so it's going to store it at 0400 on this pass. And then we can increase the value of X, and if that value isn't 0, remember the 0 flag, sorry, if it's not 0, then we just jump backwards to this label. So this says find the multi-label, which is this exclamation mark. You can put a name in here if you want, you know, something like that, but you don't have to. If you don't, it will just look for the one without it, and this minus says look backwards for that label. So this is an example of using the 0 flag to create a loop which goes through all the values from 0 to FF, increasing one at a time, and then when it gets to FF, the next time it increases, it'll go to 0, which means this flag will no longer say it's not 0, so it won't do this loop, and it'll jump to here. And that's how the 0 flag works. So I will explain the negative flag in a minute. You can see it's cleared the screen. It has written ready back in the screen, but that's because it was returned. If you didn't specify no, you have to specify in Kick Assembler. I mean, you could just put a name here like this as well, and that would do the same thing. But it's good to, I mean, I've tried to get used to putting names on my variables, on my loops like that. The reason these are good is because if you've got 2 loops, so I do this twice, why you'd want to do it twice I don't know, but say I did do it twice and I try and compile this, it's going to complain about it because it's already defined. Whereas if I use multi-labels, this is why they're called multi-labels, it allows me to use the same name. And that's useful because sometimes you just want to have lots of loops and you might just want to call them loop. You don't have to think of a new name for everything. And there you go. Can you fill the screen with a single character, and then if you change the character itself where it's stored in memory, whatever is displayed on screen is changed also? Yes, so the font is also in memory now. The default font is actually a ROM font and you can't change it, but you can create a new font, point the VIC chip at that new font and it will use that instead. I want to just quickly explain the negative flag. I think that's the only one I'll explain before I finish on the flags, and we'll move on to kind of the 3 parts that make up a game. So this would be our initialization loop. the other flag I want to look at is the negative flag. So to explain the negative flag, I need to explain 2's complement. So 2's complement is a way of describing numbers, integer numbers, that allow you to have negative numbers as well. So if we look at a binary number like this, okay, that's the maximum binary number. That's FF in hexadecimal, or it's 255 in decimal. This means that this can go from, actually let's just keep that on the same line, let's just duplicate that down. I'll do it like here. So our 8-bit numbers can go from 0 to 255, but sometimes you need a negative number. So the way this is handled is this bit here is called the sign bit. For the most part, you will probably just be using numbers like this, but sometimes you want a negative number. So what we can do is we can use this to signify that a number is negative or not. And the way this works is, if you imagine the numbers on a line from, I think it's, I can never remember if it's -127 or -128, hang on. It would be -128. So you imagine a number line that goes from -128 to 0 to 127. So at this point here, our number is, and at this point here, our number is, you can see this number is set to, this bit here is set to 0, so our number is still positive. But if we were to add 1 to this binary number, we would get this number here. And that number is -128, because now the number is negative because this bit has been set. And because it's a number line, it's just a wrapping number line, and the end number is here. That is actually this number here. And this is what 2's complement is. And then if you just keep adding numbers to this, so if we do that number is actually -1, because we've moved all the way along the line 127 times, because these 4 numbers are 127, but we've now got this bit set. And if you add 1 to this, the number will wrap around and become 0, 0, 0, and become 0. So it's good to think about it as a number line that wraps like that, so you can understand. So if you were to take 1 away from 0, this is the value you will get. It will wrap around and become all the 1s, which is -1. A little bit complicated to understand at first, but once you get used to using it, it's actually quite easy. Hi Velociraptor 6128, welcome to the stream. Hang on, let me see if I've missed any follows or anything. I did miss 2 follows actually from quite a while ago, so thank you for the follow TinySmall69, and thank you for the follow Nevermorey. Sorry for missing those. I don't know why I didn't hear those. One way to explain it is, what number do you need to add instead of subtract to make the result the same? Yeah, exactly. So so if you wanted to add a number to get to -1 from 0, you would have to add 256 to it. No, hang on. Yeah, hang on, am I looking at this wrong? Is that right? Because I think... No, that's right, isn't it? Yeah, that's what the carry flag comes out. I don't want to cover the carry flag right now. I find it easier to think of it as a number line like this. So you think of it as a number line that goes from -128 to 127. When you get to the end, you wrap around to the beginning. Likewise, if you're going backwards and you get to the end, you wrap around to here. And then it's quite easy to think about it. And just know that it's this bit here. It's the highest bit in your binary number, which is the 0 flag, which is the sign bit. And so what that does, I'm going to put a breakpoint in here so we can run through this code and just get to this point. So if I load, let's actually load it in binary. If I load that number and I load that number, you'll see what happens. And then I'm going to do the same with the number 0, and I'm just going to increase it, decrease it, and you'll see what happens. Right, so we're at this point now. We're going to load the value 7f into the accumulator. It says 7f here, but this is the actual value that we're moving in. It is still 7f, but this is binary representation. And you can see the upper bit is set to 0. So this is a positive number, which means that the negative flag up here should stay at 0. So if I just skip through that, you see the negative flag hasn't changed, it's on 0. But the next line sets FF, and FF is all ones, and that means that the sign bit is set to 1. So when I skip through, you'll see the negative flag gets set up there. I need to jump off that just in case it breaks. Likewise, if I load 0 into the X register, I've broken it now because the bloody... Sometimes it can be more of a hindrance than anything else, the debugger. So let's skip through that again and get to the X. So here's the X, load X with 0. See, the negative flag is currently on 1 because the last thing we did was load a negative number into the accumulator. If I skip through, we've now put 0 in, which is not negative because the 8th bit is 0, so it's a positive number. So the negative flag is set. So this is our X register. The next command decreases the X register. So what will happen here is this X register is going to drop from 0 to FF. And when I do that, you'll see that it sets the negative flag again. And that's because we've gone below 0. Below 0 is -1. -1 is FF. And so it's a negative number. And that's how the negative flag works. It has its uses for many things. One mistake I see a lot of people make is they will do, actually I will cover the carry flag, so they'll do something like this. Let's do it, let's try and think of how best to do this. They'll do this, they'll do a branch if minus. I'm just going to put a jump in here, it doesn't really matter. Now this will work, and the reason this will work is because internally this does a subtraction. So this is taking 32 and subtracting 36 from it, which gives us a result of -4. So the result is minus. So it looks like this is a useful way of comparing if this number is lower than this number. However, this breaks at a certain point. So if I put this in, now let's do this with 2 on that side, and let's make it really high. So you'd think this would work the same way, that this is less than this number, so this 0 flag will the negative flag will work, but it's not going to work in this case. And that's because if you take 32 and you minus E2 from it, what you get is internally the comparison is going to come up with the value. Hang on, is that right? 32. Am I going the wrong way around here? Hang on, have I done something wrong here? Let me think about this. 32. Do you know what? I'm just going to run it through the debugger. It's the easiest way to do this. Basically, you shouldn't be using minus and plus to detect that, because sometimes you're looking for things that are larger than that gap. And I've run it in the wrong thing. My brain's not working right again. Oh yes, easy 6.5. That's a good point actually. Easy 6.5.2 is a good thing I like about this though, is I can step through the code really easily and see what's going on. So if we look at the negative flag, it's set to 0. If we compare 32 to E2, let's press the right buttons. Yeah, there you go. So that is actually lower than this number, but the result is actually a positive number because we've done negative. Our result is negative. our internal calculation for the comparison. As I said, comparison with the numbers internally does a subtraction. When you subtract these values, you get negative b2. Well, negative b2 is actually a positive number because b2 itself is, let's see if I can get this right, it will be 10110010. That's b2, which is a negative number, but then we're saying it's negative, which makes it positive. So that's actually the internal result, and that's a positive number, so that doesn't work. And this is where we need the carry flag. So what the carry flag is used for is for doing arithmetic. If you add two numbers together and they overflow, it sets a carry flag, just like you would do if you were doing some addition. If you were to do some addition like 32 plus 9, then the way you were taught to do this in school is you go, okay, 32 plus 9, let's do that with underscore so it looks a bit normal. You would say, okay, 2 plus 9 is 1, carry the 1, and add it to this, that becomes 41 like that. And it's that carry is what's going on here. It's a carry flag, and it's used for that exact purpose. So you can do you can add numbers up that go beyond. So overflow, yeah, I'm not going to go through the overflow flag just yet. You probably won't need the overflow flag. It's very rare you actually need to use that, and I don't want to confuse people with that. So instead of using branch if minus, what you can do is you can use the carry flag. This is kind of really useful in branch instructions, and it's the only true way to do less than or more than. So the way it works is, the way I like to think about it, right? If you've got two branch instructions, you've got branch if carry clear, branch if carry set. Think of it this way: C is less than S. If you were to put these alphabetically, branch if carry clear is less than branch if carry. So if you were to give them numerical values of where they'd appear in a dictionary, this would have a numerical value less than this. So we use branch if carry clear to say it's less than this value. So BCC like that means is 32 less than E2, which in this case it is, so we jump to this location, and we can check that by running it in the debugger, and you'll see when this comparison instruction happens that the carry flag will stay clear. It didn't break because I didn't put a breakpoint in. Yeah, when people ask about overflow, they usually mean carry flag. Yeah, they do. The overflow is something completely different. Does the CPU really consider a negative number? Yeah, it doesn't really know about it. It's just whenever it sees that bit set, it will set that negative flag. So you can use them as negative numbers. Internally, the CPU doesn't care. The CPU is just dealing with bits, basically. It's just a way for you to have some way of checking if a number, if you want to use negative numbers, to check that a number is, you can consider a number as negative in terms of two complements. So yeah, exactly. If you're doing arithmetic operations, then they can be treated as negative numbers. Exactly. So it is a complicated topic. I'm going to do a stream fairly soon, probably not the next one. I think I might do a game dissect stream next, but I might do another one of these 6502 streams on arithmetic, so dealing with addition and subtraction, and using the carry bit to do 16-bit and 24-bit and 32-bit addition and subtraction, some techniques for doing division, obviously by powers of 2, very easy to do. How to negate a number, how to divide a negative number by 2, things like all these sort of things that crop up, because obviously when we do division by 2 you shift bits, and because the the sign bit is bit 8, you'd be shifting that as well. So there's a little trick you can do to get around that. Okay, so let's have a look at this. So we're loading the accumulator with 32 and we're going to compare it with E2, and because it's less, the carry flag will stay clear. So we'll just skip through to the carry check there, and the carry is indeed clear here. Now if we were to change this number to 22, it's the opposite. So remember what I said, you've got BCC is less than BCS, think about them alphabetically. So the opposite of this is that BCS is more than or equal to BCC. And that's what that does there. So in this case, we should see the carry flag get set at this point. I wish the CC2 debugger would remember its size as well. So let's skip through to that branch command, and you can see the carry flag is indeed set there. And just to prove that it works with equal as well, if you set the numbers to be the same, we'll do this. And you see the carry flag is still set there as well. Yeah, exactly, Agmavin. It is just it's just a representation. It's just an interpretation of the number. Internally, the number is just 8 bits. How you interpret it is it up to you. The only thing that the processor can do differently is if you set, I may as well explain this flag as well, is if you set the decimal flag, which is the D flag here. So let's have a quick look at that. So if you set the decimal flag, just so you know as well, the carry flag can be set and it can be cleared like that. You can't clear the negative flag or set the negative flag. Likewise, you can't clear or set the 0 flag. That's just a result of operations. But the carry flag you can set. Likewise, you can set the decimal flag. And what this does is something a little bit different. So if we clear the carry flag, I'll explain why we clear the carry flag. Just know for now that if you do an addition, you should probably be clearing the carry flag. And I add these two numbers together. What would you expect the accumulator to be here at this point? So if I did it without this, let's have a look and see what we get. So let's put a breakpoint in here. What we would expect here is for the accumulator to be 3-0 at this point, because if you add 1-8 and 1-8, you get 3-0. Let's run it in the debugger. And there you go, 3-0 in the accumulator, because we've taken 1-8 in hexadecimal, which is 24, and we've added another 24 to it, which is 48, which is 3-0 in hexadecimal. However, there is a decimal flag, and what this allows us to do is treat these numbers like decimal. You still supply them as hexadecimal in here, but internally what it's doing is it's saying, okay, this is actually 18. So internally it's the processor treats it as the number 18 because of decimal flag. Basically all numbers that all immediate mode numbers that it reads here, or all numbers that end up in the registers, get treated in a format that's called binary coded decimal. And what it means basically is this is your tens, this is your units. So instead of this being your 16s and your units, this is your 10s and your units. So now when we run this, what we should see is actually 18 plus 18. We should see the number 36 in the accumulator. If it runs, let's stretch this out a little bit, and there you go. You can see the number 36 there. So the decimal mode is actually, I think this is something that doesn't exist on the NES. So oh yeah, kind of disabled. Yeah, it is part of the 6502 spec, but I think yeah, Nintendo did disable it. We tend to use it mostly for scores and things. It's a really good way of just kind of working with scores and stuff in games. So quite often you might see something like this in memory. You know, I don't know. And that is actually just You know, that's some high score that's stored like that, for instance. It just makes it easy to do kind of score maths and stuff. It's not a great idea to use it if you're unfamiliar with it, because you can get into the habit of turning it on and not turning it off, or if you're using interrupts, forgetting to actually turn it off in the interrupts as well. So if you have a big piece of code that's doing this here, say you've got a loop in here that does a load of stuff, and then it clears the decimal flag, but you've got an interrupt down here, and your interrupt does some other stuff. So, you know, it might say you've got a macro to store your state. So you're storing your, like we showed before, pushing your registers onto the stack. You know, doing your but then in the middle here you do some other stuff where you might load a memory address, add a value to it, and then store it. It's actually going to do it in decimal mode, so you need to be really, really careful with it. So yeah, just be very careful with it when you're messing with it. The correct way to do that would be to use push the processor stack and pull the processor stack as well. Oh yes, and that's the other good thing to point out as well. The BCD mode is literally just for addition and subtraction, because again, internally the number is still 18 in hexadecimal. It's just that when it comes to additions and subtractions, it's using binary coded decimal to do those. So instead of adding two hexadecimal numbers together, it's adding these as decimal numbers, but internally it is still stored as you know. So if I do this here, clear the decimal flag, come back to here, I still got 36, but that value is no longer, I mean, it's not 36, the value is 54, but visually, when you know, if you're working in binary coded decimal, you are going to see additions and subtractions done in decimal mode. Incorrect Legends, they removed it to make space for more important graphic stuff. Yeah, I think they were probably afraid of patents, like you say. Oh, is this open source to Izzy? Do you mean oh, okay, yes. So my GitHub has got stuff from this stream. I will be adding this stuff straight after the stream. There's also my Let's Dissect stream, which has got some it's got various things. There's a few games in there that we've hacked around with. There's some kind of graphical techniques. We've gone over VSP scrolling. We've gone over a few various kind of demo techniques and stuff. And there's also the Let's Make a Game, which is a bit of a messy repo, but it is coming along quite nicely, which is the game that we've been working on Saturdays. It's coming along really nicely now, actually. Oh, thank you for the follow to Izzy, I missed that. I think my alerts have gone silent for some reason, because I'm not hearing them. I can hear the music alright. I can just check my properties on here. Oh no, I should be hearing it. I don't know why I'm not. That's weird. Do I use Sublime with GitHub for versioning? I don't use GitHub in Sublime. I actually use, well, it depends what system I'm on. So at the moment I've been using Source Tree to do most of my stuff on Windows. I'm using GitHub Desktop on my work laptop. But yeah, I use Source Tree because I just find I've used it a lot at work. I mean, I have switched over to GitHub Desktop at work, but I just kind of use this. Sometimes I'll use the command line, but generally I'll use this. It's just easier for me. Yeah, that's a good point actually, Jup. That is a really good common way to do lookup tables for the digits as well. 256 byte lookup tables for each digit. Would you need 256 or would you need more? hexadecimal to decimal. I was trying to think how I've always. To be honest, I tend not to do very much work in decimal anyway. Even when I'm doing debugging stuff, I tend to output hexadecimal to the screen anyway. I just rather work in hexadecimal. Can you export labels from code to device monitoring kick assembly? Yeah, you can as well. So if I change that to loop like so, and export this, and then go in here and assemble. You can see there it's got the loop in there as well, so you can see it in the code. It's really hard to see on this, so but yeah, it's definitely, it's really handy actually, and it's really nice to be able to see it in the debugger as well. If I just jump to that location, I keep putting breakpoints everywhere, god damn it. Yeah, you can see it nicely labelled there as well. Although it isn't showing it in the branch instructions. I think it does show it for the jump instructions, but I don't think it shows it for branches. Okay, I'm just going to spend the last 15 minutes to very quickly go over what you would consider to be the core components of a game. Now we've done the flags, so this would be like a setup routine. You would also, as well as kind of clearing the screen here, you might want to set your fonts, set your Vic banks. We've gone over this in other streams, so just look back at some of the other videos if you want to know how to do these things. Set graphics modes, things like that. Initialize interrupts. This is your kind of initialization phase. And then once you've done all that, you'll have a main loop. So your main loop will basically be something like this, which will perform a load of code, and then at the end it will jump back and repeat. And this may be built up of a few parts, so you could have a few different loops. It may be you've just got one main loop where you do something like jump to an intro, to a game over, like so, and so this will play the intro, and the intro function will keep running until you press fire button or something. Then it will return to here, which will jump to the game, and then jump to the game over. Or what I tend to do is I tend to have them as separate loops in here as well. So I'll have like a intro loop, and then a game loop, and then so on. And then inside your game loop, you will have something along the lines of kind of get player input, and so on. It's all just about it's all just about arranging kind of small little subroutines into loops. And if you want to see that in more detail, if you look at the Let's Make a Game streams, I think we're up to like 24 now or something. I go into these in a lot more detail. Often I only have an empty loop and have everything running into it. I used to do that. I've switched away from doing that now. What I tend to do instead is I'll have something like this. So I might have a main loop. So this is just going to run eternally, and then I might have something like a frame flag or something. And then I'll do this right at the beginning. I'll go let's call that main loop. And then what I'll have is I'll have my code that I want to run once per frame here that isn't interrupt specific. So things like player code, AI code, some update code, depends on what it's doing. And instead I use I'll have an interrupt that fires at a particular point on the screen that sets this flag, and then the first thing that I'll do here is so then my interrupt down here would be whatever it would do, whatever line it would do it at. It would do something like this, and then whatever else it would be doing on either side of that. And what that means is I can keep my interrupts really small, so I can time lots and lots of different little things. So for instance, say you've got one of the things I did in doc was I had an interrupt which cleared the screen from the middle outwards by changing 2 points on the screen. So I had to move these rasters along the screen, which meant I couldn't really do a lot in those rasters because I had to keep the timings very tight. So doing it this way meant that I could keep those tight and still have this code running at a specific point as well. Check Codebase 64. Yes, definitely. Codebase 64 is where, actually coming back to the scene, I learned most of the stuff from. So, how is music handled in a game loop? Does it just play a few milliseconds and then run the other tasks? So what it tends to be, let's assume you've got an interrupt like this, and this interrupt will fire once per frame. You'll have a routine, something like that. And what this will do is just for that frame, it'll just update the frequencies, the volumes, the wave types for the SID registers for that frame, and it does that once per frame. And that will result in, I mean, it depends on the player. Some players will do it 2 or 3 times a frame, but most of them do it once per frame. Depends how accurate you want your sound to be. But most of the SID you'll hear in games are doing it once per frame. You can do it in other ways as well. So, for instance, you might want to write music that works on NTSC and PAL at the same rate, in which case you could use a CIA timer interrupt, an NMI interrupt, or something to do that. To make sure that it always fires the same number of seconds after each one, and just change that NMI timer value to be compatible with NTSC. But yeah, you would generally call this, as Jupp says, you probably in your initialization code up here, you would do something like this, where you pass a value in. So this would be like the track number you want to play, and then you would initialize it. And then your interrupt would just play that piece of music every time. C64 could play a little game and load a game and play a little game while loading. Yeah, and that's exactly, Invader Load worked exactly like that. So Invader Load would, I mean, the first kind of things we saw like that was bitmaps on the screen. So you would see bitmaps being drawn to the screen, or you would see the colors flashing at the side of the screen. That's an IRQ loader. It just means that while the game is loading, there is something that fires constantly, so that you can do other stuff as well. And some loaders allow you to have quite a lot of time to do things. So if you put like Space Invaders into the IRQ code, then yeah, you can run Space Invaders while you're loading a game, with very minimal impact on loading times. Oh, stop the music. So the 3 parts that make up a game are usually your initialization routine, your main loops. There may be more than one main loop. You may have a different main loop for intro, game over, high score routine, whatever. And then there's the little components, the little functions that make up your game routine. So imagine this is your game loop. You would have something like, in here you might have update player, or get controls and then update player, draw player, update enemies, draw enemies. Usually you have to kind of play around with where you do the drawing just to make sure that it draws at the right point on the screen. Sometimes you get a split in the middle if you're not careful. Draw HUD. These are all just going to be very tiny little routines. Well, they can be tiny, they can be huge as well. It's so different thing in style from today. Each voiceover duration is saved, and you can document the duration counting each interrupt, play note, and check each interrupt. Yeah, the thing is today, nowadays, most of that is handled for you by the play routines that you output. It depends as well. So, I mean, some musicians you work with will just use the players that things like SID Tracker. Is it SID Tracker? The iPad one, I think it's called SID Tracker. SID Wizard, as Jup says. Goat Tracker as well as another one. Ninja Tracker, I think is kind of mini version of that. And then there's musicians that will supply their own music player as well. So they're kind of old school musicians that were doing it back in the 80s. They'd all have their own players. So when you asked them for a piece of music, you would get their player that they'd written with it as well, which is kind of cool to see as well. The musicians back then knew how to code very, very well and make very optimal code as well. Interrupts can kind of be thought of kind of threads. Yeah, they can. They are essentially allowing you to stop they're allowing you to run two kind of pieces of code almost in parallel. You do have to stop one to do the other, but you can stop the one task anywhere and perform the other one. It's like drop what you're doing and do this as well. So it is kind of like threading. If you plan on having a music and sound effects, it might be good to integrate any music as soon as possible. Yes, and I definitely recommend either SID Wizard, as Jup says, or Goat Tracker. They both have sound effect support. Because it does get, if you're trying to use something that doesn't have sound effect support, SID Tracker on the iPad, for instance, actually implementing sound effects when you've got a player that's taken control of the SID stuff can be really kind of annoying. So it's good to kind of have control over that. It's annoying you can't really get the save SID back into your music editor again. Yeah, it is a little bit annoying. I mean, if you know the format of the player, then there probably are things you could do to kind of reverse engineer it a little bit. But the problem is that's only going to work if you know exactly what player they've been written with and what player it's running on, so you know the file format of the sounds. That's going to be really difficult with many SIDs. And actually a lot of the SID players are basically small emulators. They're running 6502 code and they're just emulating the player code and running it exactly as the player is telling it to run it. So it's not like you can just look into the code for the player, because the code for the SID player itself, not the one that's run on the C64, because it's the code itself is just an emulator that runs the 6502 code. You'd have to actually understand what the player format was. Right, I think I'm going to call it there actually, guys. Thanks a lot for coming along tonight. I'm going to find someone to raid now. Hopefully you've got something out of tonight. I've kind of gone a little bit from my head. I did want to prepare a little bit before today, but I didn't really have a chance to do it. I wasn't feeling too ready to do it, so I kind of winged it a little bit. But it's gone all right actually, I think. Who have we got here? Let's raid Epic Neon Ninja Monkey. He's on. I'd like to raid him. I will get this video up over the weekend. Hopefully, I think one video's probably just gone live tonight actually. But I uploaded it to YouTube earlier. Once I'm caught up, I'll get this video up onto YouTube and make a collection, so you've got a playlist for these things. Let's go and raid Epic. And then on Saturday we'll continue with the game as well. I'm feeling, still got a bit of a cold, you can probably hear it actually, but I'm feeling a little bit better. My stomach's been good to me. So hopefully we can get a full stream in on Saturday and do some cool stuff. I do want to start thinking about a title screen as well. I keep having some ideas for that. So I'd like to kind of maybe get some music and some ideas together for a title screen, because it'd be good to kind of just take a step back from the game a little bit and do something a little bit different for once on that stream. Okay, cheers guys, let's go and raid Epic now, and I will see you all on Saturday. Good night guys.